Welcome back to Pratik Academy. In last video, we have discussed about coulomb damping. And in this video, we will solve some sample numericals based on this chapter. So before going for numericals, let's take down some important formulas. First formula is nothing but differential equation for free damped vibrating system. It is mx double dot plus cx dot plus kx is equal to 0. The next is a damping factor. It is a ratio of damping coefficient to critical damping coefficient, or C upon Cc. Then critical damping coefficient is equal to 2m omega n. Then damped natural frequency is equal to under root 1 minus zeta square into omega n, and this is for viscous damped system. Then another formula of damped natural frequency, omega d is omega n. It is damped frequency is equal to natural frequency in case of coulomb damping. Then next is a logarithmic decrement is equal to log to the base e x naught upon x1, and if ratio of amplitudes which are differ by n cycles are given, then it is equal to 1 upon n log to the base e x naught upon x naught plus n. Important is these amplitudes must be on same side. Okay. The next is for coulomb damping. Rate of decay per cycle is equal to 4f upon k, where f is a frictional force. Next is a time period of damped cycle. It is equal to 2 pi upon omega t here. Then xa, that is amplitude of viscous underdamped cycle, is equal to e raised to minus zeta omega n t a. Next is a damping force. Here this is a damping force and is equal to damping coefficient into velocity, that is cv or cx dot. This is for linear case. If you consider angular, then it will changes to damping torque or resisting torque is equal to ct into theta dot. It is angular velocity. And lastly, resistive force in case of coulomb damping is equal to mu into Rn, that is natural reaction. So based upon these formulas, let's solve first numerical. So in problem they have given this diagram, and in diagram these amplitudes are given, and these amplitudes are continuously decreasing. Then time difference between xa and xb, or two amplitudes, are given here. Weight of system is given 1 ton, and they have asked to find logarithmic decrement, damped frequency, undamped frequency, stiffness, critical damping coefficient. So let's start with logarithmic decrement. We have del is equal to log to the base e x naught upon x1. So here the total 3 amplitudes are given. We can take this as x naught, then x1 will be 2. If we take 2 as x naught, then x1 will become 0.75, or if you take 5 and after 2 cycle 0.75, then you can use another formula, 1 upon n log to the base e x naught on x naught plus n. If you want to use this formula, or if you take 5 and 0.75, then you have to use this formula. Here n will be 2. Then now putting values, our del, it is logarithmic decrement, is coming 0.9162. The next is a damped frequency. For damped frequency we have one formula, under root 1 minus zeta square into omega n, but here we don't know value of zeta or omega n, So use another formula, that is omega d is equal to 2 pi upon t. T is a time period. Okay, here this value 0.64 second is time required to come particle from its original position to again same location. So this will be time period, or this time difference is a time difference or time period. So putting value here 0.64, we get omega d is equal to 0.98, sorry 9.81 radian per second. Then next is a undamped natural frequency. So undamped natural frequency, we have formula omega d is equal to under root 1 minus zeta square into omega n. Here we know value of omega d, but zeta is not known. So first calculate zeta. For calculation of zeta, we use another formula of logarithmic decrement, that is del is equal to 2 pi zeta under root 1 minus zeta square. Okay, here we have to find out del. 2 pi is constant, 1 is constant. By solving this, we get zeta as equal to 0.1442. Okay, again after calculation of zeta, check that this zeta must be less than 1, because we have derived all these derivations for underdamped systems. Then now we have known value of zeta. Putting here value of zeta, we get natural frequency as 9.9137 radian per second. Okay, now next is a stiffness. For calculation of stiffness, we are using natural frequency formula, that is omega n is equal to under root k upon m. Here m is given 1 ton, that is 1000 kg, and omega n is we have already found out. By solving, we get k is equal to 98.281 kilonewton per meter. Then last is a critical damping coefficient. Its formula is 2m omega n. Now 2 is a constant, m is given, and omega n we have found out. So by putting these values, our cc will come 19827.4 Newton second per meter. So this is first problem, which is based upon logarithmic decrement. Now consider another problem. A body of mass 5 kg is supported on a spring of stiffness 250 Newton per meter, and it is connected to a dashpot which produces resistance of 0.004 Newton at a velocity of 2 centimeter per second. In what ratio will the amplitude of vibrating system or vibration decay after 5 cycles? So here they have given mass 5 kg, k is given 250 Newton per meter. Then this dashpot produces resisting force, so it is a damping force. It is given 0.004. So here is 0.004 Newton, and velocity x dot is 2 centimeter per second. Okay, now, and they have asked ratio of amplitude after 5 cycles, that is x naught, and after 5 cycles, so x5. This ratio we have interested. So we have formula del is equal to 1 upon n x naught upon x naught plus n. And here if we put value 5 here, then our formula changes to 1 upon 5 here, log 1 upon 5 x naught upon x5. Our formula changes to this one, 1 upon 5 log x naught upon x5. Now to find out this ratio x0 upon x5, we have to know what is value of del. So using another formula for logarithmic decrement, we get del as a 2 pi zeta upon under root 1 minus zeta square. So we have to first calculate value of zeta. Again, formula for zeta is c upon cc. Here we have known for cc we have formula cc is equal to 2m omega n. Here m is known. For omega n they have given stiffness and mass, so putting for omega n we have put under root k upon m. Here k is known, m is known, m is known, so cc can be calculated. The next remain is find out c. So we have damping force is equal to c into velocity. Okay, damping force is given 0.004 Newton. Velocity is given 2 centimeter per second, and by putting these values we get damping coefficient as 0.2 Newton meter per second. Now here we have find out c, we have find out cc. Putting these two values we get zeta is equal to 3.16 10⁻³ . Now by using value of zeta we calculated del and it is coming 0.0198, and now we have no del, then putting value of del in our equation, that is 0.0198 is equal to 1 upon 5 log to the base e x0 upon x5. Here we know here this value is known, so taking antilog here we can find out ratio x0 upon x5 and it is coming 1.104. So in this video we have seen important formulas and two numericals based upon logarithmic decrements. In next video we will solve remaining problems. If you like this video, please comment on this video, share this video with your friends. Thank you for watching.